For decades, we looked at the night sky above as a mechanism with a fixed set of rules. We saw a predictable rhythm, driven by equations that mapped the cosmos like giant cosmic clockwork. We operated on the belief that the heavy lifting was done. Albert Einstein and the 20th century's best minds had provided the baseline. Improved telescopes would simply add precision to their equations. This created the lambda cold dark matter model. It was our blueprint for a universe with a clear origin and a future of endless, infinite expansion. Astronomy had become an exercise in high-resolution bookkeeping, focused on filling in decimal points rather than questioning the nature of reality. Recently, a new generation of observatories began mapping the sky. Arrays of golden mirrors started capturing data at the highest resolution in human history. The ultra-sharp measurements from these instruments contradict the standard model we used for nearly a century. We call this the precision paradox. As our optical clarity improves, our theoretical math creates more chaos. A clearer look at the cosmos has triggered a crisis in modern physics. High in the Chilean Andes, the Atacama Cosmology Telescope spent 20 years mapping the oldest light in the universe, the cosmic microwave background. By reading the polarization of this ancient fossil light, we can calculate how fast the fabric of space is stretching. This chart illustrates the conflict. Measuring expansion via nearby supernovas gives us one specific speed. Measuring it via distant fossil light gives us a different number. These two numbers cannot coexist in our current equations. The math refuses to reconcile. Physicists call this irreconcilable gap the Hubble tension. Since space cannot stretch at two different rates simultaneously, our base model appears to be missing a major structural component. Beyond the ancient light, we are seeing present-day violent anomalies, like the Amaterasu particle. This single particle carries 40 million times more energy than the most powerful accelerators on Earth. 3D simulations of magnetic fields trace the particle back to the centers of nearby star-forming galaxies, like M82. At the same time, radio telescopes captured RB float, the brightest fast radio burst ever recorded. Astronomers pinpointed it to the edge of a star-forming region 130 million light-years away. The existence of these messengers suggests our current physical laws cannot account for matter under the universe's most extreme conditions. The most significant challenge comes from the Dark Energy Survey, which is investigating the force pulling the universe apart. Cosmologists typically assume a positive cosmological constant, a force that keeps the universe expanding forever. This chart shows the new Dark Energy Survey data. Instead of staying positive, the value dips. The survey suggests the cosmological constant might actually be negative. If this force is dynamically changing, our predictions for the end of time must change with it. A negative cosmological constant means the ongoing expansion of our universe doesn't last forever. It eventually stops completely and violently reverses its course. This model calculates that the universe will reach its maximum size in about 11 billion years. Following that peak, the universe would contract back in on itself, potentially collapsing to a single point in 20 billion years. While still highly debated, these calculations suggest the universe could have a definitive expiration date. For many astrophysicists, a broken model is an exciting development. Science often advances through these conflicts. 50 years ago, Stephen Hawking challenged established rules with the black hole information paradox. The current scientific focus is on cleaning house, identifying theoretical dead ends and narrowing the path forward. The standard model is rapidly evolving, revealing a cosmos that is significantly more violent, dynamic, and definitively finite than we ever previously believed.